Hello everyone, welcome back. So this time in Stacks we have yet another problem which looks really hard, but I promise you it's really hard. It's actually not going to be that bad. So let's try it out. So what we have here, it looks like we have some sort of bar system, and I'll change it to my little laser pointer because that's fun. A bar system, and it's got a couple moment applied at each of these points. We have a few forces as well. And wants us to find an equivalent resultant force and coupled moment at point O. So right here, the origin, we want to say, okay, one force, one coupled moment. Can we do that? Can we figure out one force and coupled that will take into account all these forces? How are we going to do that? Well, we're going to find our force by simply adding all of our forces. That's pretty simple. The reaction force right here is just going to be the sum of these forces. Our moment, a little bit more difficult. We had to add all of our coupled moments, and then we have to take into account the moment that would be caused by moving these forces from where they act on it to the origin. So if we go too far, that makes it a bigger moment. Shorter distance, small moment. And at least for this guy right here, since its line of action is on, it includes point O, there is no moment for moving it, which we would get by taking the cross product. Okay, so pause, go, try this on your own, and once you have, come back here and check it out, see if you did it right. So 3, 2, 1. Okay, so hopefully you paused, hopefully you went and did the problem rather than just watching it straight through. I'm unable to watch you, but I'm always suspicious. So let's see how it goes. First off, sum of the forces. We have 3 forces, we break them up into their components. Now, this isn't too terrible to do. First off, force 3, well, that's really nice. In fact, it is directly along the y-axis. Makes it pretty easy for us. Force 1 here is directly along the z-axis. So one component, one component. Then force 2 right here. Now, while initially you probably looked at this and you weren't noticing, but it is not along the x-axis, it's actually at an angle. And you see that it's angled downward. It is in the zx plane. So it's a 45-degree angle from the x-axis. So with that, we can begin to do this. We can solve this problem. There's actually kind of 2 fun ways to do that if you want, but we'll just do the normal way first, which is simply, you got pin out, to take that force and break it up into a triangle. Everything in this class is triangles. It always comes back to triangles. So we have our force in the x direction, we have our force in the z direction, and this is 45 degrees. And so we can then get everything, the 2 components, in terms of our force. Now, one really interesting detail about this is that since this force is in the xz plane, we can actually use our direction cosines to help us out. Because technically, sine of 45 and cosine of 45 are the exact same thing. So if I want to get the unit vector of force 2, like what direction it's pointing along, I just take cosine of the angle to the x-axis and cosine of the angle to the z-axis. And those are the exact angles because it's in the xz plane. If it was somewhere in the y direction as well, then it wouldn't work out. I needed a better angle. But in this particular case, it can work. So just a little fun detail right there. Not super important, but just an interesting thing where our direction cosines can come back. Okay, so we have this. Now, what about our position vectors? Well, to get to force 3, that's pretty easy. It's just 1.9 meters along this direction. Position 1, it's just 0.5 meters in the y direction. And then finally to position 2, we have 1.1 meters in this direction. So we have all of those. And I am noticing right now that all of these show a I, they should show a J. So don't let that confuse you because that is most definitely along the y-axis. So it might come back to bite us, but we'll find out in a minute. Oh. And let me erase some stuff because that's getting a bit too crazy here. Then finally, our couple moments. Well, we have couple moment 1, which is 100k, because it's along the z-axis. Same thing is, remember that moments are vectors as well. So if I have one that's pointing down, if it's not along an axis, I'm going to break it up using the same exact method. You see cosine 45, sine of 45? Same thing here, cosine 45, sine of 45 here. Just different magnitude. This is something multiplying by something different. The unit vector is the exact same. Okay, so now I've got to take those cross products and hopefully everything works out. So we get our forces, we add those together, and now we do those cross products. And you can see that they did fix it here. So just type on a pretty slide, but it's now in the J direction for all of those, which it needed to be. And then let's look at this and see what we find. So we have 3 forces here, and each of these forces is moved from their point to the origin. And the interesting thing we see is right here, if I cross any of these, that's 0, and that's 0. This one has no moment, and that's force 3 right there. Just once again telling us that if the line of action of your force goes through the point you're moving it to, which in this case is the point O, our origin, then there's no moment caused by moving it. You can just slide along there. They're called sliding vectors. The other two, though, do have components. They do have moments, and you can see those right here. If we take the cross product, we get, finally, in the end, 183k and 122i. And that is it. We have our resultant moment, we have our resultant force, and those are both now able to take place at the origin. And that will give us the same external effect as all of our forces and moments from earlier. So, I think that's everything. Yep. So I hope this helped. And if you have any questions, feel free to email me. Let me know. I can always add more videos if you need. So, thanks for listening. See you all next time. Bye-bye.